While learning Newton's gravitational law, we have seen that the force of attraction between two objects is inversely proportional to the square of distance between them. Why Newton has taken this inverse square dependence on distance in his law of gravitation? He was helped by Kepler's third law, and that is known as inverse square law of gravity. To understand inverse square law of gravity, first we have to understand some concept, and they are: first is uniform circular motion. Uniform circular motion, it is the motion of object performing circular motion with constant speed. Means the object is performing circular motion with constant speed. Its speed is not going to change. Uniform means constant. So if object is performing such motion, that motion is possible only due to a centripetal force which is directed towards the center of the circle. Now actually we will see how this inverse square dependence was discovered with explanation. Suppose an object is performing uniform circular motion. The mass of that object is m. It is revolving with the speed v, and the radius of the circle along which the object is performing circular motion is having radius r. Now we know that F force is indicated by mass into acceleration. For circular motion, acceleration is given by v square by r, that is speed square divided by radius. So this value we will put here. So this equation will become F is equal to m v square by r. This is for an object. Now this same concept we will apply for planets. Instead of object, just suppose this is a planet, and at the center sun is present. So all the things are same. M will be the mass of planet, v will be the speed of rotation of planet around the sun, and r is the distance between sun and planet. So for that case also, the force acting on the planet is given by F is equal to m v square by r. So for a planet performing circular motion, force acting on it is given by F is equal to mv square by r. Now in this formula, speed can be also expressed as speed is equal to distance upon time. Already this formula you are familiar with that. Speed is equal to distance upon time. Now consider distance. How much distance a planet will cover during one rotation, that is to complete one rotation around the sun? That distance will be 2 pi r, because it is circular in shape. So the speed or the distance covered by planet in one revolution will be the circumference of circle, and that will be 2 pi r. How much time it will take to cover one revolution around the sun? That will be capital T, which will be the time period of that. So now this value of V we will put in the formula of force. So it will become F is equal to m. Instead of V, this value we will put. So 2 pi r divided by T whole bracket square, and this is divided by r. This whole brackets square we will do. M 2 square 4 pi square r square whole divided by T square, and this is divided by r. Now this r square and r will get cancelled. Only one r will remain in the numerator. Now we know that in Kepler's third law we have seen that T square divided by r cube is equal to constant. But in this formula just we are having r. So if we want to get r cube, we have to multiply by r square. So that r square and r, it will be r cube. But this will change the step. That's why we have to divide by r square also. So just we have to multiply by r square and divide by r square. So the equation will become m4 pi square r into r square r cube divided by t square r square. Now we are interested in this t square and r cube. So we will make it separate and all other terms we will take separately. m4 pi square divided by r square into r cube divided by t square. Now according to Kepler's third law, t square by r cube is equal to k. But here this term is opposite, r cube by t square. So it will be 1 upon k. So instead of r cube by t square, we will write 1 upon k. So the equation will become m4 pi square divided by r square k. Now for any object, its mass, value of pi, value of this constant remains same or it is constant. These terms are constant. Variable term is just this. So we can write as 1 upon r square into whole, this is constant. That's why this force is inversely proportional to r square, or it is inversely proportional to the distance between two objects. And thus Newton concluded that the centripetal force, which is the force acting on the planet, is responsible for its circular motion, must be inversely proportional to the square of distance between the planet and the sun. Newton identified this force with the force of gravity and hence postulated the inverse square law of gravitation. The gravitational force is much weaker than the other forces in nature, but it controls the universe and decides the future. This is possible because of the huge masses of the planets, stars, and other constituents of universe. In this way, Newton's assumption related to inverse square dependence was verified.
Newton's inverse square law. Mathematical form of inverse square law is F is proportional to 1 by r square. Proof. Suppose a planet moves around the Sun in a circular orbit of radius r. If v is the orbital velocity of the planet, then the centripetal force acting on the planet is given by F is directly proportional to mv square by r. Equation 1. Where m is the mass of body, v is the orbital velocity, r is the radius of the circular orbit. As mass of planet is constant, hence F is proportional to v square by r. If planet completes one revolution around the Sun in time t, then velocity of the planet is v equal to 2 pi r by t. V square is proportional to r square by t square. V square is directly proportional to 1 by r into r cube by t square. According to Kepler's third law, r cube by t square equals constant. V square is proportional to 1 by r. Put in equation 1. F is proportional to 1 by r into 1 by r. F is proportional to 1 by r square. R is the radius of the circular orbit. This shows that gravitational force between Sun and planet is inversely proportional to square of distance between them.
Our next point is Earth's gravitational force. Whenever any stone or ball you are throwing up in the sky, certain questions might be arising in your mind, like, will the velocity of stone thrown vertically upwards remain constant, or will it change with time? How will it change? Why doesn't the stone move up all the time? Why does it fall down after reaching a certain height? What does its maximum height depend on? Like these questions. Answer for this is, the earth attracts every object near it towards itself because of the gravitational force. The center of mass of earth is situated at its center. So, the gravitational force on any object due to the earth is always directed towards the center of the earth. Because of this force, an object falls vertically downwards on earth. When we throw a stone vertically upwards, this gravitational force of earth tries to pull it down, and due to this its velocity reduces. Means when, suppose this is the stone or ball, when it goes vertically upwards in the sky, its velocity reduces, and when it reaches a particular point, its velocity becomes 0, and after this point it starts to come down and it reaches to the earth's surface. So after this point, when velocity becomes 0, the stone starts to moving vertically downward towards the center of earth under its influence, that is under the influence of gravitational force. Thus, if the earth attracts an apple towards itself, the apple also attracts the earth towards itself with the same force. Because what universal law of gravitation states, each and every object attracts each other. That is, a small thing or a small stone also applies the gravitational force on earth, and earth is also applying the gravitational force on that stone. Why then does the stone fall towards the earth, but the earth does not move towards the stone?
We saw that the gravitational force is the attractive force between any two objects with non-zero mass separated by a distance. So does the apple fall towards the earth, or does the earth move towards the apple? Or do both move towards each other? It's actually simple logic. This is the earth, and say this minuscule object is an apple. Based on what we learnt about the gravitational force, both apply an equal force to attract the other object towards itself. So if the forces are equal, which one will accelerate more? Based on the Newton's second law, we know that the force applied is the product of mass and acceleration. So the acceleration will equal force over the mass. The acceleration is inversely proportional to the mass. If the mass is more, the acceleration will be lesser. As the mass of the earth is much more than the mass of the apple, it is the apple that accelerates towards the earth and not the other way around. Hope that makes it clear.
The gravitational force due to earth also acts on the moon, because of which it revolves around the earth. Similar situation exists for the artificial satellites orbiting the earth. The moon and artificial satellites orbit the earth. The earth attracts them towards itself, but unlike the falling apple or falling stone, they do not fall on the earth. Why? This is because of the velocity of the moon and satellites along their orbits. If this velocity was not there, then they would have fallen on the earth. Same reason is behind the flying of aeroplanes. Aeroplanes also should come down after some time, na? But this is not happening because the aeroplanes are having velocity. They are moving with speed. That's why that speed overcomes the gravitational pull of earth and they can fly up in the sky. But the stone or ball, they are not able to overcome earth's gravitational force or pull. So they are coming downwards. So by seeing this video, I think you got the answer why all objects on the surface of earth are moving towards the earth and why earth is not moving towards that object. Because force is equal to mass into acceleration. So acceleration will be force divided by mass. So from this equation we get that acceleration is inversely proportional to mass. If mass is decreasing, acceleration will increase, and if mass is increasing, acceleration will decrease. So in this way, if mass of the object is less, it will accelerate more. Accelerate means it comes in motion. So if mass is less, it will start to accelerate. That object will come in motion. So in this way, the smaller objects are getting attracted towards the earth, though they are applying some gravitational force towards the earth. Next point is Earth's gravitational acceleration, which is denoted by small g. Newton's second law, last year you have studied. What is its statement? If a force is acting on moving object, it results in acceleration. That is, if the force is acting on any object which is in motion, due to that force, acceleration will be generated in that body. So this Newton's second law we can apply with the Earth's gravitational force also. Earth is applying gravitational force on every object. So because of this force, there will be production of acceleration. That acceleration is called as Earth's acceleration due to gravity, and which is indicated by small g. Gravitational force of Earth produces acceleration, that is called acceleration due to gravity, which is indicated by small g. Now question is that whether this acceleration due to gravity is vector or scalar. As this acceleration due to gravity depends upon force and force is vector, so acceleration due to gravity is also vector. Next is direction of small g. As gravitational force of earth is directed towards the center of earth, acceleration due to gravity is also directed towards the center of earth, that is vertically downwards. So we will summarize what we have learnt about acceleration due to gravity. Acceleration due to gravity indicated by small g, it is produced due to Earth's gravitational force. It is a vector quantity and it is directed towards the center of the earth. Now we will calculate value of acceleration due to gravity on the surface of earth. For that, consider the object of mass m at a distance r from the center of earth. So this is the center of earth and the object is placed here, whose mass is small m and it is at the distance r. This distance will become capital R because this is nothing but radius of earth, as it is the distance from center to the object, that is center to the surface. So it will become radius of the earth. Now the gravitational force acting on this object will be given by Newton's law of gravitation, and that will be F is equal to capital G, capital M, small m divided by r square. Here objects are two. First object is earth and second thing is the object present on the surface of earth. So this capital M indicates earth's mass and small m indicates object's mass. Now we also know that force is nothing but product of mass into acceleration. But as this force is related to gravitational force of earth, this A will become acceleration due to gravity. So this is our equation first according to Newton's universal law, and this from the definition of force we know this formula. Now both the side F or force is same. So these two sides we can equate. So G M divided by capital R square is equal to M into small g. So this M is present on both the side, it will get cancelled. So G we will get as gravitational constant into mass of earth divided by radius of earth's square. Now by equating the two formulas for force, we got the value for acceleration due to gravity is gravitational constant into mass of earth divided by radius of earth and its square. Now we know that gravitational constant, its value is discovered as 6.67 into 10 raised to minus 11 Newton meter square per kg square. Mass of earth is approximately 6 into 10 raised to 24 kilogram and radius of earth is approximately 6.4 into 10 raised to 6 meter. So all these values we are having. Now just these values we will put in this formula. So after putting all the values, equation will become like this. If we will solve this, then we will get answer value of G as 9.77, and as it is nothing but acceleration, so unit will be meter per second square. So value of acceleration due to gravity on surface of earth, its value is approximately 9.77. From the formula you can see that this acceleration due to gravity is dependent only on mass of the object and radius of the object, because the value of gravitational constant is always same and it is 6.67 into 10 raised to minus 11. So value of G is dependent only on mass of the object and radius of the object. That's why acceleration due to gravity on different planet is different. Next point is variation in the value of acceleration due to gravity. First point is change along the surface of the earth. Before learning this point, just consider once again the formula of acceleration due to gravity. Acceleration due to gravity is dependent only on mass of the object and radius of the object, that is distance of the object from center. So if distance of object from center increases, acceleration due to gravity will decrease, and if distance will decrease, then acceleration due to gravity will increase. Like that, mass is in numerator, that is it is directly proportional. If mass increases, acceleration due to gravity increases. If mass decreases, acceleration due to gravity decreases. So remember these things. Distance from the object and center, this is inversely proportional to acceleration due to gravity, and mass of the object is directly proportional to the acceleration due to gravity. Our first point is change along the surface of earth. Value of G is not same everywhere on the surface of earth. Why this is so? Because the shape of earth is not exactly sphere. If we will look the shape of earth, it is bulges at equator. Equator is the middle line. This line is shown as equator. So you can see that it just flattened at both the poles and it is bulges at the equator. So if you will see distance, suppose the object is here on equator, this distance is larger, and suppose the object is on the pole, this distance is smaller. So what will happen if the object is on equator? That is, distance is increased from center. As distance increases, gravity will decrease. So here acceleration due to gravity is having small value, and here on the poles, if you will see on both the poles, as distance from center and the object is smaller, what will happen according to this relation? If distance decreases, acceleration due to gravity increases. So on the both the poles, gravitational value has acceleration due to gravity has larger value, because radius of earth is largest at equator and it is smallest at the pole. The value of g is thus highest at poles, and that is 9.832 meter per second square. As we move from pole towards the equator, value of g starts to decrease because the radius also starts to decrease. That's why at the equator the value of g is smallest, and that is 9.78 meter per second square. Second point is change with height. What is the effect if the height is changed on acceleration due to gravity? Acceleration due to gravity formula is g is equal to gm upon r square, where r is the radius of earth, and this formula is for when the object is on the surface of earth. So here we can use r, that is radius of earth. But if suppose condition is like this, the object is now not on the surface of earth, but it is at somewhat height above the surface of earth. So here what will happen? This distance r we can't take in this formula, because here now distance from center to object will be what? This r, and above the surface up to this object height is h. So this total distance from object to center will be given as r, small r is equal to capital R plus h. So here this formula just get modified like this: small g is equal to g m upon r plus h bracket square, where this is the object which is lying above the surface of earth, and this is when it is on the surface. Now what is the change we will see? Here also we can see that as distance increased from the surface of earth, value of acceleration due to gravity will decrease as distance increases. Thus as we go at higher heights, acceleration due to gravity will decrease. But suppose the object is at the height nearby the surface of earth, that is the distance is negligible as compared to radius. For example, suppose aeroplane is flying at height 10 km above the surface of earth. Total distance of that aeroplane will become, radius of earth is approximately 6400 km, and that height above the surface of earth is 10. So the total distance of the aeroplane from the center will be 6410 km. Now if this value you will put in this formula, the value of acceleration due to gravity will change, but that change will be very negligible. So if the objects are revolving near to the surface of earth, or they are near to the surface of earth, then the value of gravitational acceleration due to gravity will change, but that change will be negligible. But for the artificial satellites which are orbiting in the sky at higher heights, for example approximately 32,000 km above the surface of earth, artificial satellites are revolving. For that cases, change in the acceleration due to gravity is considerable. For example, I will show with the help of table. Here you can see the table. On the surface of earth, height will be 0 because that object is on the surface of earth. So acceleration due to gravity, its value is approximately 9.8. Mount Everest. At the peak of Mount Everest, so here distance will change. We have to take r plus h, that is radius of earth, plus 8.8. So here you can see value is 9.8. That is, the change is negligible. That's why value is same. Maximum height reached by man-made balloon. That height is 36.6 kilometer. Now here you can see as distance is increased, the change in the acceleration due to gravity is somewhat considerable. Typical weather satellite which are revolving at 400 kilometer, for that acceleration due to gravity will become 8.7. And the communication satellites which are revolving at 35,700 kilometer, for that acceleration due to gravity, its value will be 0.225. So as we are going to higher heights, then acceleration due to gravity decreases. Next factor we are going to consider about acceleration due to gravity is change in depth. Suppose we are on the surface of earth and we are going inside the earth now. So what will happen? The radius of earth will start to decrease. Suppose at this point the radius will decrease. Here if you will reach, the radius will decrease. Now just as radius is decreasing, what will happen? Acceleration due to gravity will increase. But actually this is not happening. Why? Because when this radius is decreasing, suppose you are at this point inside the earth. At that point earth will be of this shape. So its mass will be also reduced. Again suppose you are at this point, its radius will decrease. At the same time mass will also decrease. And when you will reach at the center, what will happen? The radius will become 0 and the mass of earth will also become 0. So both the values mass and radius will become 0 and 0. That's why at the center of earth the acceleration due to gravity is 0. So as we are moving inside the earth, radius is decreasing and also mass is decreasing. That's why as combined effect of these two decreases, acceleration due to gravity is not increasing but it decreases. And when we will reach at the center, both mass and radius will become 0. That's why value of acceleration due to gravity at the center of earth will be 0. Now one question is that might be you have seen the astronomers when they are walking on the surface of moon, they are looking like they are jumping. Why this is happening? Because acceleration due to gravity of moon is different than earth. Every planet and satellite has its different mass and radius, and we know that acceleration due to gravity is dependent on mass and radius. So acceleration due to gravity of moon is about 1/6 of value of earth. That is, it is reduced by 6th factor than the acceleration due to gravity of earth. As a result, using the same amount of force, we can jump 6 times higher on the moon as compared to that of on the earth. So just we will summarize what we have learnt about variation of acceleration due to gravity. Change along the surface of earth. Due to bulging at the equator and flattening at pole, value of G is lowest at equator and it is highest at pole. Second is change with height. As the height is increasing, value of acceleration due to gravity decreases because they both are in inverse relation. Next is change in depth or change with depth. As we move inside the earth, mass of earth also decreases and radius of earth also decreases. So due to this two decrease, the acceleration due to gravity also decreases. And at the center of earth, gravitation acceleration is 0.
Earth's gravitational acceleration. The Earth exerts gravitational force on objects near it. According to Newton's second law of motion, a force acting on a body results in its acceleration. Thus, the gravitational force due to the earth on a body results in its acceleration. This is called acceleration due to gravity and is denoted by g. Acceleration is a vector, as the gravitational force on any object due to the earth is directed towards the center of the earth. The direction of the acceleration due to gravity is also directed towards the center of the earth, that is, vertically downwards. Think about it. 1. What would happen if there was no gravity? Answer. 2. What would happen if the value of g was twice as large? Answer. Value of g on the surface of the earth. We can calculate the value of g by using Newton's universal law of gravitation for an object of mass m situated at a distance r from the center of the earth. The law of gravitation, F is equal to g m upon r square. Equation 3, m is the mass of the earth. F is equal to mg. Equation 4, from equation 3 and 4, mg is equal to g m upon r square. G is equal to gm upon r square. Equation 5, if the object is situated on the surface of the earth, r is equal to radius of the earth. Thus, the value of g on the surface of the earth is g is equal to gm upon r square. Equation 6, the unit of g in SI units is meter per second square. The mass and radius of the earth are 6 into 10 raised to 24 kg and 6.4 into 10 raised to 6 meters respectively. Using these in 6.673 into 10 raised to minus 11 into 6 into 10 raised to 24 upon 6.4 into 10 raised to 6 square is equal to 9.77 meter per second square. Equation 7. This acceleration depends only on the mass m and the radius r of the earth, and so the acceleration due to gravity at a given point on the earth is the same for all objects. It does not depend on the properties of the object. Can you tell what would be the value of g on the surface of the earth if its mass was twice as large and its radius half of what it is now? Answer. According to Newton's law of gravitation, g is equal to gm upon r square. If the value of g is doubled, g is equal to g2m upon r upon 2 square is equal to 8 gm upon r square. Thus, the value of g will increase by 8 times. Variation in the value of g. A. Change along the surface of the earth. Will the value of g be the same everywhere on the surface of the earth? The answer is no. The reason is that the shape of the earth is not exactly spherical, and so the distance of a point on the surface of the earth from its center differs somewhat from place to place. Due to its rotation, the earth bulges at the equator and is flatter at the poles. Its radius is larger at the equator and smallest at the poles. The value of g is thus highest, 9.83 meter per second square at the poles, and decreases slowly with decreasing latitude. It is lowest, 9.78 meter per second square at the equator. B. Change with height. As we go above the Earth's surface, the value of r in equation 5 increases and the value of g decreases. However, the decrease is rather small for heights which are small in comparison to the Earth's radius. For example, remember that the radius of the Earth is 6,400 kilometers. If an aeroplane is flying at a height 10 kilometers above the surface of the Earth, the distance from the Earth's surface changes from 6,400 kilometers to 6,410 kilometers, and the change in the value of g due to it is negligible. On the other hand, when we consider an artificial satellite orbiting the Earth, we have to take into account the change in the value of g due to the large change in the distance of the satellite from the center of the Earth. Some typical heights and the values of g at these heights are given in the following table. C. Change with depth. The value of g also changes if we go inside the Earth. The value of r in equation 5 decreases, and one would think that the value of g should increase as per the formula. However, the part of the Earth which contributes towards the gravitational force felt by the object also decreases. This means that the value of m to be used in equation 5 also decreases. As a combined result of change in r and m, the value of g decreases as we go deep inside the Earth. Think about it. 1. Will the direction of the gravitational force change as we go inside the Earth? Answer. 2. What will be the value of g at the center of the Earth? Answer. Every planet and satellite has different mass and radius. Hence, according to equation 6, the values of g on their surfaces are different. On the Moon, it is about 1/6 of the value on the Earth. As a result, using the same amount of force, we can jump 6 times higher on the Moon as compared to that on the Earth. Mass and weight. Mass. Mass is the amount of matter present in the object. The SI unit of mass is kg. Mass is a scalar quantity. Its value is same everywhere. Its value does not change even when we go to another planet. According to Newton's first law, it is the measure of the inertia of an object. Higher the mass, higher is the inertia. Weight. The weight of an object is defined as the force with which the Earth attracts the object. The force F on an object of mass m on the surface of the Earth can be written using equation 4. Therefore, weight W is equal to F is equal to mg. G is equal to gm upon r square. Weight being a force, its SI unit is Newton. Also, the weight being a force is a vector quantity and its direction is towards the center of the Earth. As the value of g is not same everywhere, the weight of an object changes from place to place, though its mass is constant everywhere. Colloquially, we use weight for both mass and weight and measure the weight in kilograms, which is the unit of mass. But in scientific language, when we say that Rajiv's weight is 75 kg, we are talking about Rajiv's mass. What we mean is that Rajiv's weight is equal to the gravitational force on 75 kg mass. As Rajiv's mass is 75 kg, his weight on earth is F is equal to mg is equal to 75 into 9.8 is equal to 735 Newton. The weight of 1 kg mass is 1 into 9.8 is equal to 9.9 Newton. Our weighing machine tells us the mass. The two scale balances in shops compare two weights, that is, two masses. Use your brain power. 1. Will your weight remain constant as you go above the surface of the earth? Answer. Two. Suppose you are standing on a tall ladder. If your distance from the center of the earth is 2r, what will be your weight? Answer.